let's say that a gold coin is worth G in whatever currency we're measuring it in. And then we're told that it is X% more than a silver coin. Now, if it was 5% more, then the multiplier would be 1.05 because essentially we've got 100%, we're adding 5%, we're going to get 105%, which is 1.05. What you do is you change 5% to 0.05 and then just add it onto 1. Essentially by doing 1 plus 5 over 100. So in the case of X%, it's the same idea. It's going to be 1 plus X over 100. And then we're going to multiply that by however much a silver coin is worth. So that is the first equation that we can write down between G and S. Then it says that a silver coin is worth Y% less than a gold coin. So let's do a similar example with numbers. 5% less is actually going to be 0.95 as a multiplier because we have 100% and then we're minusing 5%, 95% or 0.95. This could be 1 minus 5 over 100. In this case, it's going to be 1 minus y over 100 times by g. Now, we can combine these together. This is a sort of a simultaneous equation in some ways, I suppose. I don't think you really need to think of it like that, though. But I can replace s by this bit here. Therefore, g is going to equal 1 plus x over 100 times by 1 minus y over 100 times g. Now, I could just treat this purely as an algebraic question from here on. I can actually cross out the g's, and we've got this equation to solve where where x and y are integers. But I want to talk about the practical applications of this because I think it's quite interesting, and I'll also bring it back in at the end. Because what we're actually trying to find is all the different positive integer pairs where if I increase an amount by a percentage and then decrease that new amount by a different percentage, I'll get exactly back to the start. So I'm going to give you an example of this. Let's say I've got 100 and I increase it by 100 by 25%. Then it would go up to 125. Now, if I then decrease that by 20%, I'm now finding 20% of this new amount. It's a larger amount. So actually 20% I need to divide through by 5 would actually be 25. And I would get back to the start. So this is in fact is going to be one answer later on. X is 25 and Y is 20. We'll see it happen. But I'm just trying to explain that is what is going on. And there's going to be lots of other possibilities, but they have to be whole numbers, remember. So that is going to be a condition. So returning to this equation, I've divided through by G. I've got 1 equals. Now, I think the next thing to do is get rid of the fractions. So I can times through by 100. And when I do that, I need to times one of these by 100. Well, actually, I have to only try times one of these by 100. So let's say I times the left-hand bracket. I'm going to get 100 equals 100 plus x times 1 minus y over 100. And then I can multiply through by 100 again. Actually going to get 10,000 is equal to 100 plus x times 100 minus y. Now this kind of equation is known as a diophantine equation, and it's already in the right sort of form. I'm just going to do a little example of a different diophantine equation to illustrate it, because if you got stuck with this problem, maybe with a little bit of just a little hint now, you'll be able to carry on with this. That's the aim of these videos. At times, like you can watch the whole thing if you want, but you can also just pause and then try it yourself. So let's say I've got this equation here that I am trying to solve. Okay, this is a diophantine equation as well. I'm saying that x and y, I want to know all the different values of x and y. That's a whole numbers. Well, the way to do this is actually to factorize it. I can write it as x and y. That'll give me my x, y. And if I put a -2 here and a -2 here, then I'll almost get this, but I'm going to get an extra +4. So I'll need to -4, or I could just say it's equal to 4 there. I can -4 equals 0, but then I can rearrange it. This is how you deal with these equations, basically, because now the brackets have to be whole numbers. So I only need to look at the different factors of 4. So we've got x -2 and y -2. So we could have, say, 4 and, wait, that was going to say y minus 2, not y minus y. We're going to have 4 and 1, and 1 and 4, and 2 and 2. These are going to give some different values for x and y. So I'm now going to have to add 2 to these. So I'll get 6, 3, and 4. And then add 2 to this, I'll get 3, 6, and 4 as well. Actually, in this case, I didn't specify that they have to be whole numbers, so I'm going to also go with -1, -4, and -2. These are all my different, it's not quite the factors, you have to include plus and minus as well. So then I'll get -4, -1, and -2. Then adding 2, 1, -2, -2, 1, and even 0 and 0. So that would be my sort of complete set of solutions to this diophantine equation. Returning to this red equation here, it's actually already been factorized. So I just need to look at a similar sort of setup to what we did with the purple. I'm going to write it out again. So 100 plus x. I'm going to put this on the left-hand side now, and then 100 minus y is equal to 10,000. Okay, now remember, in this case, we've got x and y have to be greater than 0. They're not going to be like double negatives or anything going on. So that actually brings an extra little condition to this. This is always going to be greater than 0, therefore. And this one over here is going to need to be greater than 0, which means that y, in fact, is going to be between 0 and 100. Because I'm doing 100 minus y here. So that's just an extra condition we need to think about. Right, now for 4, it was it was quite quick to just write down the different sort of factor pairs. For 10,000, it's going to be a bit more involved. Now 10,000, remember, is 100 squared, which is actually 10 to the power of 4. And then we can use prime factorization and write it as 2 times 5 to the power of 4. So 2 to the 4 times 5 to the 4. There's a little trick to work out the number of factor pairs. You take the power and you add 1 to it. So it's going to be, and then the same with this one, you times them together, in fact. So actually, there's going to be 25 factors for 100. We just want to find the ones where y is between 0 and 100. So 100 minus y is also between 0 and 100. So let's write these down in a list, a little bit like before. In the answers, they just write down the factors straight away. I'm going to show you how we can work them out. So we'll start with 10,000. This is going to be a solution. And then it's got to be 1 to multiply to 10,000. Now what I did is I just then repeatedly divided by 2 and times by 2. Okay, so I've still got my 10,000 in there. So this would be a solution. Okay. And here I get 625 and 16. I can't divide by 2 anymore. So I'm going to start again with 10,000, but this time I'm going to divide through by 5. And times this one by 5. So these will all work. And now I'm going to divide by 2 again until I can't anymore. And times by 2. Okay, now I'll take my 200 and divide by 5. And then if I carry on, I'd get 100 and 100, right? But this is where I'd have to rule this one out. Okay, it might be a solution to the diophantine equation, but it will not give y greater than 0. It'd actually give y equal to 0. So if we take the 400 and divide by 5, we'll get 80. and then here we get 200. So we're sort of at that point swapping around, and actually y 100 minus y is greater than 100 plus x, which I'm not interested in. So actually, those are all my solutions for x, not x and y, but 100 plus x and 100 minus y, and hence those are the number of solutions for x and y. I'm going to work them out in a minute, but in terms of this question, we can now answer it because how many have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that makes sense because we had a solution where we had 100 and 100. Remember, we had 25 factors, but that, we had got this one where they're the same. And then we've got 24 factors left over, but only half of them, um, values of x are going to be valid, and half the values of y are going to be valid because of that extra condition. So to solve this question, the answer is going to be 12. I'm going to talk a little bit more. So I'm going to actually write down the different values of x and y now based on these. So in the case of x, I just need to minus 100 each time, which I will now do. Okay, and in the case of y, I'm going to do 100 minus 100 minus y. Basically, it's going to this and the y one are going to add up to 100, so I'm going to get 99. Okay, those are our solutions for x and y. And finally, I'm just going to bring it back into the application. So what we are saying is if we increase any number, let's focus on the one I did at the start, any number by 25% and then decrease it by 20%, I'll get back to the start. But these are all the other integer values. Well, exactly the same will happen if I increase a number by 100%, so double it, and then I decrease it by 50%, that will get me back to the start. Some really wait, I think that was, yeah, some really interesting ones. If I increase by 525% and then decrease by 84%, you wouldn't expect that one. We get back to the start. So these are 12 different cases where it will happen. So yeah, I really like this question. We kind of move away from it and solve it using the methods shown, but it's got a real application. And yeah, like you see questions like this creep into math challenges sometimes. It's like if you had two rectangles, if you had like, yeah, rectangle, and then they got the same dimensions, and then I increase the base by 1.25, what would I have to decrease the height by, or something like that? Actually, yeah, just one rectangle, but it illustrates the point. You'd have to decrease it by 20%. You get back to the start, and these little pairs are all the different ways it can happen. So of course it does relate back to the gold coins and the silver coins, but it's like more of a general idea that you can apply. Increasing by a percentage and decreasing by a different percentage gets you back to the start. These are all the different ways you can do it, where x and y are whole numbers. Brilliant. Okay, well done if you tried this question. Um, it's tough, I think, but I think a really rewarding solution. And hopefully next time you see something like this, you'll be even more confident. And yeah, well done.